The proof of step 3 is somewhat technical, and in order to be able to construct such a function z, we need to create two tables, and the aim is to see what kind of choices we can consider to construct such a function. So, in other words, in step 3, we want to see that for given distinct places, P1 up to P, and then the given integers and functions by i's. First, let me choose an integer such that valuation of the functions of given yi's at any place is bounded below this integer. Or more explicitly, for each I and j, if you consider this condition, if you write it explicitly, since each valuations of the functions are integers, it is always possible to find the integer n that will be a lower bound for these integers. And let me state these conditions as table 1. And depending on this S, and by step 2, so here call this step 2 guarantees the existence of a function omega such that V1 of, when we shift 1, we get it is strictly bigger than R1. Still, we're in the same given Ri's, and Vi omega is bigger than Ri for the remaining places. So here, instead of taking the integers as R1 up to Rn, for fixed S, we may also consider the integers Ri minus S. And by using the existence of such a function, actually we can guarantee that there are n many functions. In other words, by step 2, we can choose n functions, omega i's, that satisfies these two conditions. Again, this condition seems a bit ugly. Let me write it explicitly in a table. We want to see the existence of omega 1 up to omega n. This satisfies, whose valuation satisfies these inequalities for each places. Rn minus S, Rn omega n minus 1 is bigger than Rn minus S. And let me call it table 2. And let me here also note that, for instance, the existence of omega 1 can be set when we consider this condition. And similarly, we can see the existence of omega 2 that satisfies the conditions in step 2. So that means we are able to say that there exist n functions which gives the desired property. So by considering these omegas, and here also note that this S depend on the choice, the integer we consider that satisfies this property. Now our claim is that if we set sum of the product yj times omega j, here yj's are given in the assumption. These are the yj's in table 2. Our claim is that z is the desired function that satisfies the property in claim 3. In other words, if you consider the valuation, it's not, by the way, evaluation. What I want to mean by valuation is the image under the discrete valuation map. Valuation of z minus yi is bigger than the given integers ii's. And to see that, for instance, let me consider the evaluation z minus y1. I write this term explicitly with minus y1, and I want to look at if its valuation can be bounded by r1. Here we will take y1 parenthesis and we will apply triangle inequality for the discrete valuation map. And again, for these products, we will use the property of the discrete valuation map. So that means we can write it as sum of their valuations. Now, from table 1, we know the existence of S which bounds this integer. So that means V1 of Y1 is bigger than or equal to S1, S. And from table 2, from the first condition, we know that this is bigger than R1 minus S. So sum of these two integers then should be strictly bigger than R1. And similarly, we also see that from the table 1 and table 2, in that this minimum is bounded below R1. And similarly, you can also check indeed it holds for every Ri. And this z gives us the desired function in claim 3. But here note that to complete the proof, we need to see that it should be an equality instead of inequality. And to complete the proof, now our aim is that given pairwise distinct discrete valuation maps, there exists a function, and of course, given functions xi's and the integers ri's, our claim is to show the existence of the function such that x minus xi has prescribed poles and zeros counting multiplicity. And here let me note that from claim 3, we can choose a function vi of z minus xi is bigger than ri. And here also recall that discrete valuation map is onto. So that means this is always possible to choose a function zi, vi of zi is equal to given integer ri. Again from claim 3, not claim 3 by the way, step 3. We also know that there's a function z prime minus this zi's, given zi's, has valuation bigger than ri. Now here let me observe that valuation of z prime at pi can be computed by adding the term zi's, and here these two, so here the valuation of this term is bigger than ri, and the valuation of this term is equal to ri because zi are chosen with respect to these integers, so they don't have the same values under the discrete valuation map. That means we can apply triangle inequality, strict triangle inequality, and similarly by this fact, this minimum is equal to ri. But here we want to see that z minus xi or x minus xi should satisfy this equality. And for this purpose, we will set the function x as z plus z prime. And by computing the valuation of x minus xi, again by the same argument, valuation of this function is bigger than ri, and this is ri, we can apply strict triangle inequality. complete the proof. So if you consider such a function x, we are able to, we may interpret it this is a function that approaches the given functions xn's or x minus xi's as describe poles and zeros, counting their orders. And as a consequence, only by using the fact in the step 1 of the theorem of this previous theorem, we will see that set of places in an algebraic function field is infinite. And we prove it like in the elementary algebraic elementary number theory when we want to show that there are infinitely many prime. That means, let me suppose not. And suppose that we have only finite many places in the set of places PF. And by step 1 in the proof of the previous theorem, we can choose a function set which has a 0 at P1 and poles at other remaining places. Now, by using this function, let me set the function as x as z plus 1. And here note that v1 of z is positive because we choose the z with respect to this property, and valuation of the every constant is 0. We can again apply the strict triangle inequality, and we see that v1 of x is 0, and similarly for the other remaining places from to up to n, we choose z such that vi of z is negative, and this is 0, so that means it is less than 0. But this fact, so we suppose that we have empty places, and for the function x, for all places we only get poles. So that means x is not a constant, so it's independent of this valuation. And since these all integer values are negative, it has only poles. But this is not possible because by corollary 1,120, we know that x has at least one pole and 1 zeros. Let me denote it by Q. And in this case, VQ of x should be bigger than 0. And this shows us there's a place which is not in the set of places we considered here. And this gives us contradiction. So that means the set of places are infinite.